they didn't compare A to B, C to D, B to C, A to G.
So ANOVA, when you run ANOVA analysis, all what you get a p-value that's less than the alpha. This means that the results are statistically significant. But all what you know at that point is that there is a difference somewhere between the groups. Could be between only two groups, or between all groups, or a couple of them. In order to know where the difference exactly lies, you have to run individual comparisons, like the example in the slides. You have to run A versus B, B versus C, C versus D, A versus D, and so on, all possible comparisons to see where the difference exactly lies. And could be between more than two groups, and we call it pairwise comparison. Okay, good. Number two. So this is the same results from Stata from the slides. It was comparing the mean forced expiratory volume, FEV1, between the study groups using ANOVA, and the resulting p-value was 0.0520. So first, is that statistically significant or not? Are the results statistically significant or not? No, they are not. Why is that? Why the results are not statistically significant?
Because p is greater than the alpha.
And what was the alpha here? What was the alpha value?
0.05.
Why did you assume that?
Because that's what we assume.
So if the alpha value was not provided, then you should have assumed it's 0.05, and because the p-value is greater than 0.05, then there is no difference, or there is no statistically significant difference. As you probably heard in the narrative that was accompanying the slides, when we get a p-value that close to 0.05, we usually suspect that there might have been something wrong in the experiment, that if you really inspected very well and tried to find what was like the design, what was the sample size, how did they run the study, and all of that, you might be able to figure out some underlying problem in the design, or not. Maybe it's just not statistically significant. But just be careful when you get a p-value that's that close to the alpha. But technically and formally, if it's greater than 0.05, then it's not significant. Remember that we said it's either significant or not. There is not such thing as marginally significant or not significant or any of that. So the correct answer will be there is no difference between the group means since p-value is more than alpha b. Okay, when using ANOVA to compare means, if the variation between groups is a lot bigger than the variation within groups, that suggests that there are differences among group means. True or false?
Wow.
False? Anyone answer false? Okay. So it's true, and that's exactly, I don't want to get you into the details, and we're not going to talk about the details of that because we don't want to teach ANOVA in a mathematical approach. But basically, the way ANOVA runs in the background, the way the software does it for you, they first see what is like the standard deviation in each single group. So if we have groups A, B, C, and D, they look at each group and see the standard deviation in each group. Then they square that, which is the variance in each group. If you remember, the variance is the square of the standard deviation. And then they also see the variability or the variance between groups, between different groups, not within groups. And then they actually compare them. If the variation between groups is much bigger than the variation within groups, then the results are statistically significant. You don't have to worry about that, you just need to know the concept, how it runs behind the scenes. But all what you get in ANOVA that you should care about is the p-value. Is the p-value, is it less than alpha? Then the results are statistically significant, and then you indicate that there's at least one mean that's different from the rest. That's all what you need to pay attention to. but I just wanted to let you know how it is conducted. If we go back actually to this table, so if you can see, that's what the software does when it calculates analysis of variance. They calculate the variance or the sum squares between groups and within groups. And actually, if you look at this F statistic, it's like the Z statistic or the T statistic. It's basically that they compare these two together and they get this number as a result. And then they give you the p-value. But again, all what you care about is the p-value. Okay, so what are the two correct hypotheses, null and alternative hypotheses for this example? Is A correct? Okay, so this is a null hypothesis. The mean blood pressure is the same because remember the null hypothesis is a no difference hypothesis. There's nothing going on. There's no difference. So number A is the correct null hypothesis. What's the correct alternative hypothesis? D, any different answer than D? Okay, so D, that there is actually a difference between at least two of the groups, right? Not between all groups, at least between two of the groups. That is the alternative hypothesis. So if you remember also from the example in the slides, the null hypothesis was that mu1 equal mu2 equal mu3 equal mu4 and so on. So all of them are basically the same. There is no difference between the population means. And the alternative hypothesis was that at least one mean is different from the rest. Number 5, we have 3 groups here to compare. What's the test that we to compare the mean, the mean difference or reduction in weight? What is the test we use to compare these means? C, analysis of variance. So what do we use A for, the Z test? For comparing what? What do we use the Z test for then?
Two sample proportions.
When you're comparing the means between two groups.
No.
T-test.
What do we use the Z test for? Comparing what? Two sample proportions. So proportions in general. So we use Z test to compare proportions, and if there are more than 2 proportions, we use chi-square. Remember that. So what do we use the t-test for then? Sample means, and when do we use the Bayer t-test?
Crossover, yeah.
And the Bayer t-test, we use it for dependent groups or related groups. If we have one group that we test before and after, or at multiple times, the same group, that's called Bayer t-test or dependent t-test. And this is very important because we are actually gonna have a similar measure in ANOVA today that's called repeated measures ANOVA. Repeated measures ANOVA is an extension of the Bayer t-test. Things are gonna be really easy and fun, hopefully today. So before we start the applications, I want to go quickly over these 7 or 8 slides. And then maybe you can take a little break and then start working on the application. So you all agreed that when we run ANOVA and get a p-value that's less than the alpha, all what we can conclude at this point is that there is at least one mean that's different from the rest, but we don't know which one is different and which 2 groups are different, right? So that's why we run what's called a post hoc analysis. Post hoc analysis means after running the initial or primary analysis, we run a secondary analysis to see which groups are different from each other. In the example in the slides, you saw that figure and you also saw that one. And the difference between these two, if you use the mean, if you draw the mean in any statistical software, it gives you the mean and it gives you a little bit extension like this, and this extension is basically the standard deviation of the mean. So that's a plus minus a standard deviation. So that value will be the plus and this value will be the minus, because remember that there is still some level of error in any estimate that we observe, right? And that's why when I provide you sometimes with the mean blood pressure, I say plus minus standard deviation. And if we draw the mean in each group, like the non-smokers, the moderate smokers, the heavy smokers, the light smokers, and so on, if we drew all of them like this, there is actually an informal way, look at the word informal way to visually inspect this data and be able to detect if there is a difference between certain groups. But remember, it's an informal method just for yourself to get a preliminary idea which groups are different. But can you actually write it up in a paper or say, just I visually inspected the data and I found that these two groups are different? No, you cannot. You have to run a formal statistical analysis in order to reach that conclusion. But if you look at these standard deviations, there is a common rule that if they actually overlap with a different group, it means they are not actually different from each other. So the means are not different. So basically, if you look at these three, do they overlap or not? The standard deviations, do they overlap or not? They do. And this means that actually these three are not statistically different from each other. But again, remember that this is just a visual inspection, it's an informal analysis. You cannot make the same conclusion, write it up in a paper without running the numbers. How about this one, the non-smokers, and the second one, I don't remember what's the BS, what was it? Passive smokers. So are these different from each other, the non-smokers and the passive smokers?
Yep.
Yes.
Yep, they are, because look at this, the standard deviations do not overlap. There's a space between them, they do not overlap. So probably, I would say probably they are different from each other. How about the non-smokers and the moderate smokers and also the heavy smokers? Do they overlap? No, they do not, which means what? They are statistically different or different from each other. But again, this is just all an informal analysis before we run an official analysis. Same about light smokers and moderate smokers, they do not overlap. So that's a way, an informal way to look at the data and be able to kind of preliminarily tell if the groups are different from each other or their means are different from each other or not. Sometimes we do not actually describe the data in means and standard deviation, as you remember. We describe it as median and interquartile ranges. The median is similar to the mean, we just calculated a little bit differently for certain types of data. Sometimes it represents the data in a better way, but it's the same thing. The only difference here is that we look at the median. This is a median, and if you remember from the descriptive statistics, this is the 25th percentile, and this is or the first quartile, and this is the third quartile. And what we will be looking here when we're comparing the three groups, we will see if these two edges are overlapping with the other group or not, the first and the third quartile. So if you look at these two groups from two medical centers, the third quartile here is actually overlapping with this one, which means they are not different because they are overlapping. There's no clear white space between them, right?
Yeah.
Which means they are not different. Same here, there's overlap as well here, so it means they are not different. If this one was, was really up high from them, like the first quartile would be, above the third quartile here, this would mean that they are different. So again, if we visually inspect this, it would mean that the three of them are not actually different from each other because they all overlap. The boundaries overlap, if you want to call them this, their boundaries overlap. I'm not going to ask you in the exam to make a conclusion about this, but I just wanted you to know if you just don't have time and if you see data at the first glance and you want to make a quick conclusion about if the groups are different. If you're in doubt, you would definitely have to run the analysis, but I'm not going to put you in a situation like this in the exam. Okay, so again, after finding a statistically significant difference among the groups using ANOVA, it is expected that the researcher would be curious and interested to know which groups are different from each other. Again, in order to do that, we do post hoc pairwise group analysis. We compare each two groups at a time. However, there is a little problem. And when we compare them, by the way, just want to bring your attention to something tricky that I might ask in the exam. Remember when we said that chi-square is used for comparing more than two proportions, but we also said that it can still be used to compare two proportions, right? Same here. ANOVA can compare more than, is actually designed to compare more than two means, but it can still compare two means, right? But the alternative is not true. Like t-test cannot be used to compare more than two means. But ANOVA can be used for comparing two or more means, while t-test cannot. Is that clear? So that's why when you're running the pairwise comparisons between groups, you can use either a t-test because you're comparing two groups, or ANOVA. That's fine too. It's no problem. However, there is a little problem that wasn't in the slides. Remember when we're comparing two groups, let's say we're using the regular alpha, the 0.05, right? And that is a type of error. You have accepted the 5%. You have accepted that 5% of the time, the results that you see might have happened by chance, correct? But that was for only two groups and one comparison. You were running one comparison only. But when you're running in the same experiment, you start running multiple comparisons between the groups. It would be unfair to use the same level of error because you're doing more work basically, and so the chance for committing more error is what? It's higher, right? Instead of running one test, one comparison, if you have A, B, C, D groups, you're running now A with B, A with C, A with D, B with C, B with E, and so on. So you're running multiple comparisons, so your error is no longer only 5%. That would be unfair and incorrect, in fact. So you need to adjust for the multiple comparisons you're running by also adjusting the level of error. And we're going to talk about this in a second. But you can no longer use a 0.05. And this is really, really, really important for you to understand, because I'm not going to ask you that level of details in the exam again. To run it, I might ask you just theoretically. But it's really important because when you're reading a paper and they have run multiple comparisons, they are going to tell you what they have used to fix the alpha level to make it right, and you have to understand what they have done. So statisticians have developed several tools to adjust for this increasing error probability when you're running multiple comparisons. Two of the very famous methods are called Bonferroni's correction method. This is very important. You're going to see it in a lot of paper. They will say we have used ANOVA, one-way ANOVA, with Bonferroni correction. Bonferroni correction means that they have run multiple analyses and corrected the alpha level. Or there is a Tukey's HSD test. HSD stands for highly significant. I don't remember the acronym. What the acronym stands for. Highly significant, something like it. I don't remember honestly what it is. Honest significant something test. But anyway, you will see it as Tukey's HSD, or sometimes just Tukey's. And this is very important. We're actually going to use it today to run post hoc analysis. So what happens in the Bonferroni's method? In the Bonferroni's method, it's really, really easy. They say, how many comparisons do you have? You just count how many comparisons do you have. So if we have, let's say, 3 groups, how many comparisons do we have? It's going to be A with B, A with C, and B with C. Right? Any more? Is that it? Okay? So what do you basically do? How do you adjust the alpha level now? You basically divide the alpha level that we know, which is 0.05, or whatever alpha level you have used originally, and you divide it by the number of comparisons. So you will divide 0.05, if the alpha was 0.05 originally, you divide it by 3, and that would be your new alpha level. How about if we had 4 groups? How many comparisons do we have? We have 4 groups. 6, right? So we have 6 comparisons, so you divide the 0.05 by 6, and that's your new alpha level that you're going to use to make determination if the results or the difference between the means in two groups is statistically significant or is not. So that's the Bonferroni correction method, and we're going to have an example in a minute. How about the Tukey's HST test? The Tukey is run by the software. You don't have to adjust the alpha or do anything. Basically, it adjusts the type of error. Behind the scene, you don't see what happens. You just select that you want to use Tukey's HST test to run post hoc analysis, and it does all the work. You don't have to manually correct the alpha. You still stick to your original alpha level. So remember, that's the major difference. Today, using an online tool, we're going to actually be using the Tukey's HST test, so you're not going to be making any adjustments. You're going to just select Tukey's and run pairwise comparisons and compare all groups using the original original alpha level. So in the smoking examples, remember there were 6 groups, so the total number of possible pairwise comparisons was 15, for example. So again, if we compare all these groups in pairs, like non-smokers versus light smokers versus moderate smokers, and we still use the 0.05 alpha level, we would be mistaken. We have to correct the alpha level using Bonferroni's. We would divide 0.05 by 15, the number of comparisons, and you will get a new alpha level of 0.003. As you can see, it's much smaller, it's more conservative, because basically it decreases the probability of error when you run multiple comparisons like that, and that will be your alpha level. So if I give you in the exam, if I give you an alpha level, just an alpha level, and I give you the number of comparisons or the number of groups we're having, and I ask you to correct the alpha level using Bonferroni's method, you should be able to do that. Divide the alpha level by the number of comparisons and give me the new alpha level that we should be using for the experiment. That's all that I'm going to be asking you to do. Okay, so we're past the post hoc analysis. For the Tukey's, we're going to do lots of applications, and that will explain it much better. The Tukey's, you don't have to do anything actually. You just run the analysis, it will give you the results. But I wanted to also talk to you about the types of ANOVA that we use. The ANOVA that we have been talking about so far is called one-way ANOVA. And the reason we call it one-way ANOVA is that there are actually two-way ANOVA and multi-factor or three-way ANOVA and four-way ANOVA and so on. Why do we call it one-way ANOVA? Does anyone know? I can guess. Why do we call it one-way ANOVA?
Just look for it.
There's only one factor.
So there is only one factor that we're comparing. Like we're comparing the difference of an FEV of FEV, the mean of FEV1 between the two groups. But we're not comparing anything else. We're assuming by doing this, we are assuming that everything else is the same, is fixed, that there are no other variables that are different between the groups. Otherwise, remember, that adds to the potential of confounding or bias. If there are other different aspects or characteristics that are different between the groups. So when doing one-way ANOVA, we're assuming that the groups are similar, but we're just testing or evaluating this one factor. For two-way ANOVA, we're changing two factors at a time. So we might be comparing two factors at a time while everything else is fixed. And you can do or you can apply the same thing about three-way ANOVA and multi-factor ANOVA and so on. What we're interested here in this class is just one-way ANOVA, but you have to know that there are other types and what do they mean. Now, this is the last concept we want to cover, repeated measures ANOVA. Again, as I told you in the beginning, repeated measures ANOVA is an extension of t-dependent or pair t-test. And remember, in t-test, dependent t-test, we used to compare a group before and the same group before and after an intervention. So we're not studying independent groups. In repeated measures ANOVA, the only difference is that we're considering 3 assessments, more than 2 assessments or more than 2 means. Otherwise, we would be using dependent t-test. So what is a repeated measures ANOVA? Again, it's a one-way ANOVA, but for related or paired comparisons. And there are two situations that where you can apply repeated measures ANOVA. First example is change in mean in the same group over 3 or more time points for the assessment. So for example, if you have one group and you want to assess the effect of a 6-month exercise program on blood pressure, but at just 3 different points in time, that's repeated measures ANOVA, because there are 3 groups, so you're comparing the mean blood pressure between 3 groups. That's why you're using ANOVA. And why is it called repeated measures ANOVA? Because you're assessing them at point A and point B and point C, but they are the same group. You're just comparing 3 groups at 3 different points. Or it can be actually difference in mean under 3 or more different conditions. So the same group, for example, can eat different types of cake, chocolate, caramel, and lemon, and rate each. But it's the same group rating these 3 cakes. So you're going to compare the rating between the 3 types of cake, which means again you have 3 means, because it's going to be a scale for cake 1 and cake 2 and cake 3, and you're going to have 3 means to compare, but it's the same group, and that's still repeated measures ANOVA. It wouldn't be repeated measures ANOVA if you got 3 different groups and you asked each to test each of these, taste each of these cakes. That wouldn't be repeated measures ANOVA, because now the groups would be independent. And these are very important concepts for you to know. This is just a graphical representation of the same 2 experiments I just explained. So this was the first one. Notice that this is the same group, it's just subject A, B, C, D. These are not groups, they are just the subjects in the group, same subjects here, and then at point 2, at point 3, and we assess their blood pressure at 3 different points, time point 1 and 2 and 3. But it's the same group composed of the same subjects. And we'll get the mean blood pressure here, number 1, mean blood pressure 2, mean blood pressure 3, and compare the 3 means, and that is repeated measures ANOVA. The second example about the cake was also the same group, but the same group will test the chocolate cake, and then they will go same exact group that taste the caramel cake, and then they will taste the lemon cake. And on a scale for the taste, we will get the mean here, the mean for the second cake and for the third cake, and compare which one tastes better for them. Make sense? Okay. So that's all I guess. Any questions before we start the applications? Questions? Okay. Let's take a break until 10, and then come back and start working on the applications. Before you leave, the applications are on Canvas, and I have scratch paper here, so I'm going to give you scratch paper. You're going to answer, there are 6 applications, you're going to answer them using the online tool. We're going to do one together, or maybe just give you another example other than the 6. We're going to do it together. You're going to turn in your individual work, remember, with your name, staple your sheets together, and give them to me. But you can still consult with your team if you like work with them, but you turn in your individual work. And when you come back from the break, I can show an example about how to use the online tool.
I'd use that in undergrad.
Hopefully, you break it this time when you all log in. Okay.
Just all my undergrad classes. Menus so low.
That was Thank you.
We're supposed to eat healthy.
Huh?
We're supposed to eat healthy.
Wait, speak for yourself.
See, I was so close to pick Coke. And I was like, no. Pick Pepsi. Starting this session.
You gotta start doing it. You make that roast? No?
Okay, have you all opened the applications to Canvas? Okay, and I hope that you all have scratch paper. I'll just go quickly over how we're gonna work on these applications. So of course, you know, these applications, all of them, the 6 of them, involve more than 2 groups or 2 means to compare. Since we're discussing ANOVA here, and all of them are one-way ANOVA. There's no repeated measures, none of that. It's just one-way, simple ANOVA. And for each of these applications, I don't actually ask a question anymore, and I want you to, assume or understand that it's implied that you're basically comparing the means for whatever outcome is reported for each application. That's basically what I'm asking. Is there a difference? This is the first question. Using ANOVA, is there a difference between the means of the groups? How are you going to answer this? Using ANOVA. We'll show you how to run it now. And what will you get to answer that question? What do you expect to get? A p-value. So you're going to run ANOVA, you're going to get a p-value, you're going to use this p-value to compare it to alpha. And in all these examples, alpha is fixed, 0.05. So the p-value you're going to get, if it's less than 0.05, what are you going to conclude? There is a difference between the means or the groups. If it's greater than the alpha, which is 0.05, you're going to say there is no difference between the groups, and that's the end of the story. So if there's no difference, you're not going to proceed further, right? Because if there is no difference, there is no need to run a post hoc analysis, correct? So you're going to end there. So what do I want you to report in each example? After you run it and using the online tool, you're going to report the p-value, and please put a square or rectangle around it. Okay, so I can see it clearly. This is your p-value, and then the second thing you're going to report, statistically significant or not significant. Just 2 words: p-value, statistically significant, statistically not significant, or there's a difference between the means, or there is no difference. Actually, I would prefer the latter. There is no difference or no difference. Again, if there is no difference between the means in the study, there is no reason to go beyond that and run any further analysis, Tukey's test. If there is a difference between the groups, then you would assume that the next step would be to run the pairwise comparisons between individual groups using Tukey's and tell me which specific groups are different. Like if we have A, B, C, D, which ones are statistically or significantly different from each other. I'll show you a quick example about the tool. So you click on that link or the one in Canvas as well. So for the first applications, you can see we have actually here just 5 different groups: the rheumatoid arthritis, and then the lupus, and then the third group, osteoarthritis, whatever. So they are 5. Sometimes the data will look like something like that. So if there are 2 columns for the same group, it means it's just a continuation of the data. So you're going to have to enter this data from the first column and then continue to enter the second column as well. If it has one column, then you just enter this column in the online tool. It's okay, sometimes one group would have more data than the others, and that's perfectly fine. There is one here that's a little bit tricky, in case you see this one, just again, A, B, C, D, you just enter the data as S, or here, non-smokers, light, moderate, heavy. Here's, if you see negative, you just enter it as S, because sometimes negative means a decrease in CD4 count, or a decrease in bone mineral density, or something like that. You just enter it as S. This one is a little bit tricky, because where are the groups here? How do you define the the groups that we're comparing here actually? Do you see actually three groups here? Do you see three groups? We just actually have two groups. Is that actually an example of an ANOVA? Are there three groups? Let's read the example here. The purpose of the study was to evaluate the difference in CD4 cell response in patients taking highly active therapy, treatment 1, and patients taking this therapy, treatment 2. But there is no treatment 3 or anything. Can we use ANOVA here? Still use ANOVA? Yeah. Actually, yes, we can. Yes, we can. Because remember, I told you ANOVA can be used to run also or to compare two means, right? Didn't I tell you this? This is very important. I guarantee you I'm going to have a question about it in the exam. But t-test cannot be used to do the opposite, okay? So how do we run it? How would you know which is group 1 and which is group 2? Basically from here. So if it says 1, you enter it in group 1. It's a little bit just tricky here. If it's group 2, you enter it in group 2. If it says treatment 2 here, okay? And you can still use ANOVA, okay? Is that clear to everyone? Any questions about that? Okay, here it's just group 1, 2, 3 as normal. So now let me show you the tool. And I can actually run a quick example here. So this is a tool, you all opened it. I can run a demo actually that's different from the examples. You have to choose the K, and remember from the slides, the K is the number of groups you're having. If you're having 2 groups, you're going to choose 2. And you see that although it's an ANOVA tool, it's still allowing you to compare 2 groups because it knows that ANOVA can be used also for 2 groups, right? So, or you can choose 4 or whatever, and you have to uncheck this box, because if you check this box, that's what I'm going to do now, actually to keep it a check, because I'm running a demo just to show you. It just runs a demo to show you how to use the tool, but you have to uncheck it when you're actually doing the applications. So for now, I'm going to keep it on, and then I'm going to say proceed. Basically what you do, you will get a number of columns according to the number of K you choose. So if you chose only 3, K equal 3, you're going to get 3 of these columns, not 4 to enter the data. And the way you enter the data, you can either enter them separated by commas, the numbers separated by commas, but I don't prefer this tool, this method, or you enter each number in separate line, okay? I prefer that you enter it this way. And then once you enter all the data, all what you basically do, click here, calculate ANOVA with 2 keys. And then you're gonna get lots of data. I don't want you to look at any of that. All what I want you to find is this p-value, remember? This p-value here, for example, means it's really small, right? So it's definitely statistically significant. So there is a difference between the mean of these four groups. But now we want to know if there is a statistically significant difference, we want to know which groups are different between the 4, right? So you keep going and you look at the 2-key HSD test, and then it will give you a table like this. The green ones are the groups that are significant. The other ones are not significant. So it tells you that A versus C is significant. There is a difference between the means in A versus C, A versus D, B versus D, and C versus D. The other ones are not statistically significant. What I want you to report to me, not this whole table, just write the groups that are statistically significant. So tell me, depending on the example, which groups are statistically significantly different from each other. Okay? Is that okay? Any questions? Sounds fun? Okay? Questions? Sorry, wait, please. Can we listen?
You said we should put the negative values the way it is. Do you mean we should put the negative before the null?
Yeah. Okay. It's part of the data. So if the data has a negative number, you put it because when you read the example, you will know why it makes sense. A negative would mean either a reduction in something like CD4 count, or it would mean a reduction in bone mineral density or something like that. So if there is a negative number, you put it as is. So basically, when entering the data, there are no technicalities honestly here. You just have to be accurate, paying attention, enter the data each in one line, and then run the data. If the p-value shows a statistically significant difference, then you continue to run the 2 keys to see which groups are different from each other, and you report that to me. If the p-value is not statistically significant, you stop there, and that's the end of the story for that application. Sounds great? If you're done, you're free to go. If you have any questions, please let me know. Don't be stuck.
So for this application 1, it has 2 columns for rheumatoid arthritis. You just enter all that. I'm guessing so.
That's gonna be a house.
I'll just put snap mine on 2 separate ends and one smaller.
We starting off with application 1. I know he jumped to like application 5.
I wonder where they have more values for group 1.
So there's 4 groups on this one, is that right?
There's 5. Wait,
Yeah, 5.
5, yeah.
Oh, yeah, 5.
I always feel like I'm missing one when I do this.
How do I wish I had a number pad?
Oh no.
People even don't talk to me.
I want everyone to be entering the data. I don't want you to divide the tasks. No division of the task. Remember, it's an individual application. I'm just asking you to consult or allowing you to consult with each other, but you are doing your individual work.
I'm confused on how I selected K equals 5 but only got 4 boxes.
You gotta uncheck that box.
Oh, okay. Oh. That's obnoxious.
You've been trying to figure that out this whole time?
Oh no.
Oh.
I've been entering.
Questions?
Everyone, please take a look here. Look at that. You all have one of those.
Yeah, number pad.
All have one of those.
I knew you were
That would be nice. Oh, no internet connection.
He takes that thing everywhere he goes.
Huh?
He takes that thing everywhere he goes.
Keyboard?
No, that whole computer. Wait, what the crap?
Yeah, it's not working. It's crashed on me.
It don't work.
Oh, there it goes.
I'm not gonna. If you refresh it,
Yeah,
I'm not gonna do all that again.
that was scary. We overloaded it for a second.
Oh, please enter your input data over again. No. There is an error in your input data parameters.
I'll just send you the tab.
You can copy and paste it.
Yeah.
It says one of my.
Is any of this actually sending it to me? Oh my gosh, never mind.
It says you can't put blank or like negative numbers in there.
Oh, it does.
That
It
was,
says that?
Well,
the heck?
when I read the thing, it says one or more of your inputs is either an invalid number, or it's 0, or a negative number, or entirely blank outside the domain of
Yeah, that's what I got.
Yeah.
what did
You got
what did you
it?
say?
Let me try it again.
See, it says a negative number, so can you not put negative numbers in it?
Yeah, you can. Go back.
You submit it again. Go back and see.
Go back and submit it again.
I went back. I thought I was going to erase it, but it didn't erase.
Speak for yourself. Mine erased.
It erased.
1-8-4.
Yeah.
1848. You can just go off the wire.
Okay.
The other ones are like 10 numbers. It's
Okay.
not that bad.
I'll send you something magical.
So,
Angry.
did y'all get y'all's to go?
Yeah. P value. You want to write it down?
Said p value
0.1848.
1848.
1848.
I didn't know it would string them all together and hurt me. I'll put them in separate with like inners and everything. It's just one long list of all of it. It's kind of obnoxious.
Not statistically different. That's how we put right those two things.
In any of them, yeah. They're all.
Let's go.
state it?
Not
There's not
statistically
statistics.
different.
Oh, 0.1848.
Yeah.
Okay, this is already
Guys doing okay?
Yeah, ours like the site crashed a second ago.
Oh.
They just go back. I promise I entered in all of the data and then it erased it.
No, that's okay. Trust me.
Okay.
I know they are, generic websites, and they're not very trusted, but that's all we got. Better than nothing, right?
Exactly.
I wish I could have. I've been asked for the $1,000 software.
I'm sure we should.
Right.
I
I'm sure
used
they
this one
have
in
that,
undergrad.
Uh,
This is what we used.
Okay, so the p-value
Or
is greater
papers.
than the alpha, so there's not a statistically significant difference between any of the groups, right?
Yeah, they're all red,
Yeah.
all not significant. Alpha is 0.05 again.
I think
Because
you
in
said
the
it's for all of them.
yeah, in the Tukey, though the Tukey, you don't adjust it to alpha level.
Tukey.
Yeah,
And it's because p-value is greater than alpha, right?
yeah.
There we go. So I just did 3 bulletin points. Is that what y'all are doing? So I said it's not significant, and the reason why is because the p-value is greater than alpha. And then I reported the p-value. And that's all we need to do.
When it's not significant.
yeah.
I need Ben's keyboard.
Yeah, I'm gonna go get a USB keypad.
It's kind of mechanical keyboard. You can hear that across the room. I'm so glad I know the numbers on the keyboard. I know. It'll take forever.
hold on. I'm gonna tell you. Like you not gotta write. It's less than half. So I'm going to just H now. So it's less than half. There is a difference.
Yeah. And then we put which one is significant, which one is not, right?
No, he just wants to know where the difference is with what he said. So just put the green.
Yeah, which group is significant?
The green.
There's the green.
Yeah, that's what you're saying.
Oh, it did adjust the p-value for comparison to groups A and D.
Which one we have it?
No, so the one posted I'm looking for. Oh, it's already on here. Okay.
Did y'all notice that? Wait, what? I can definitely see why we don't do this ourselves, because it doesn't make sense. Like some groups are using different p-values, like different alphas.
Does it say there's an alpha change?
No, it's just like right here, you get the output,
So do
like
we only
that's their alpha
report the
there
ones
and
that are
there, but the
significant?
overall alpha
So
is
it's only
0.05 still,
So A versus C and A versus D.
which is weird.
A versus C and A versus D are the only two groups that are statistically significant. Okay, so we don't need a report.
Nope. I'm going with
Oh, e to the negative 7? Ah. It's a really small p-value. Oh my gosh, they're all different. Except for B and C.
Oh, yeah, that's
okay. So they
Can I have your attention for a second? So when you have groups like non-smokers, light smokers, moderate and heavy, I expect you, like technically absolutely I expect you when you're comparing the different individual groups to say non-smokers is different from light, for example. I'm not saying this is the answer. Light is different from moderate, not A versus B and B versus C. You know, wait for it. Okay, so that's what I would have expected from you. I know some of you have already done it using symbols A versus B and B versus C, and that's okay. Don't worry about it. Don't fix it now. But I'm just saying for the exam. And if you're writing a paper, you don't tell people A versus B and B versus C if you have an actual name for the groups. Thank you.
Well, that's what he told us to do.
Yeah.
When he went over.
What's up for application 2? It's literally A, B, C, and D. Yeah, so.
Yeah, that's what we need.
Oh, 4.
No, we have directions up at the top of who, 20 to 45 year olds. We can make
Well, he
it.
said no. He said no. You've already written it.
Oh, I see what you're saying. Yeah, you could do that.
Okay, so p-value is like super duper small, 3, right? That's what y'all got?
Oh, yeah. He doesn't want any of the values from the results, does he?
He didn't mention them. He just said report which groups are statistically significant.
I worked in the break.
Mine did that earlier when I was uploading the T-Rex.
No, all the ones go together and all the twos go together.
So this is the second.
Treatment. All the ones are one group and all the twos are the second group.
Yeah, that was annoying.
Look, it should look like
There he goes, it came back.
Zero point 0.3485. Stop rounding.
Well, if you go down to whatever, everything.
No difference. So what you think?
Yes, it's not significant.
Zero point 534.
0.05.
Yeah, 340.
Yep.
That sucks. I'll be pissed if I ran a study and I got that. So is that it?
So no difference again?
So none of them had differences except for application 2 and 3.
Huh?
Only application 2 and 3 had any differences.
Yeah.
So, okay. Which ones did y'all like? So was 3 and 2 the only ones that had?
Yeah.
Then checked out, I guess we'll find there's a difference.
Again? Yes. 0534.
Is that like wanted us to do?
That's it.
Seems too easy.
I think he said it was gonna be easy.
Seems kind of pointless to do. I understand why we're doing it, but it's busy work.
So just our name and our team number? Well, I put it on there just.
I'm a study cardio.
This one's right.